Hey guys, the purpose of this video is to go over example 1 from your notes on limits that are evaluated numerically and graphically. Example 1 is a rational function, and I just want to take a minute to remind you of how to graph a rational function. You may remember this from accelerated pre-calc or even accelerated geometry B, algebra 2. But we want to just briefly review how to graph this function. As I mentioned in class, you're not going to always have to graph functions in calculus, but it's really important to be able to look at an equation and understand its characteristics. So the first thing we need to do is to factor our function. So we're going to take 2x squared plus 5x minus 3, the numerator, and factor that. You may remember that we have previously in the past taught you to factor using the diamond method. So we multiply 2 times negative 3 to get negative 6, and then we use the coefficient of the b term, which is 5, in our diamond. And then we ask ourselves what two numbers will multiply to give us negative 6 and add to give us 5. Hopefully you can find those two numbers easily, and that would be 6 and negative 1. When we multiply those, we get negative 6. When we add, we get 5. Now, because the leading coefficient is something other than a 1, we need to divide both of these numbers by that leading coefficient and reduce. This helps us determine our factors. So since 6 over 2 reduced to 3, that tells me that my first factor will be x plus 3. And then the negative 1/2, we do a bottoms up. The 2 that's in the denominator becomes the leading coefficient of the x. So this factor is 2x minus 1. All right. Then we need to factor the denominator to get our reduced function f of x. Hopefully you recognize x squared minus 9 as the difference of two squares. So this factors as x plus 3 and x minus 3. All right, so now we look to cancel terms or factors, and the x plus 3 and the x plus 3 we cancel. So our reduced function f of x is 2x minus 1 over x minus 3. Now you need to remember that any factors that cancel produce holes in our graph. So we're going to have a hole at x equals negative 3. That's whatever makes that factor 0. Negative 3 would make x plus 3 0. But we also need to identify the ordered pair of this hole to have a more accurate graph. So we're going to take negative 3 and we're going to plug it into our reduced function f of x. So I will plug this in and do 2 times negative 3 minus 1 and divide that by negative 3 minus 3. So hopefully you can do that without your calculator and get 7 over 6. Now 7 over 6 is a little over 1, so when we plot this hole, it'll be somewhere about right there. So there should be a hole. There you go. All right. Now you need to recall that any factors that are left in the denominator after factoring and reducing, any factors left in the denominator, that x minus 3, we have to consider what will make that 0, and that would be x equals 3. So it is not possible for x to be 3 in this function, and what that does to the graph is it produces a vertical asymptote. So over here at 3, we need to draw a vertical asymptote. Okay, now we're getting there. We need to examine some more characteristics of our function to get a complete graph. You need to recall what it takes to make a horizontal asymptote, and to find horizontal asymptotes, recall that you should compare the highest power in the numerator to the highest power in the denominator. Since these two degrees are the same, we use the ratio of the leading coefficients. So we have a 2, and the leading coefficient here is a 1. So that tells me that the horizontal asymptote occurs at y equals 2 over 1 or 2. So I'm going to draw my horizontal asymptote at 2. Just to help make this a little more accurate, it'd be nice to know where this graph crosses the x-axis, maybe to find its x-intercept, or you could even find its y-intercept. To find the x-intercept, we need to allow y to be 0. So we're going to set our reduced function of 2x minus 1 over x minus 3 equal to 0. We're going to plug in 0 for our y. Remember that when you have a fraction, though, the only way it can equal 0 is if the numerator equals 0. So we really only have to worry about where 2x minus 1 equals 0, and that's 1/2. So when x is 1/2, y is 0. So that's an ordered pair on a graph, and it tells us where it crosses. If we plug in 0 for x, we would get 1/3, and that would give us our y-intercept, which makes sense that those are close together there based on what we already have. So remember, as you sketch this graph, we've got that hole, and then the behavior of the function is that it will hug the horizontal and vertical asymptote as it approaches it. Okay, so we do need to make sure there's not more to this graph, and we do hopefully remember characteristics of rational functions, and there should be another branch either in the top portion or the bottom portion that's to the right of the vertical asymptote. So at this point, I would just test a point. I'm going to evaluate 8. So I'm going to find f of 8. I just randomly picked 8. I could have picked any number to the right of 3, but I picked 8. I'm going to plug 8 into the function, my reduced function. 2 times 8 minus 1 over 8 minus 3. So that looks like that's going to be 15 over 5, which is 3. So when x is 8, y is 3, and that just gives me an idea of where the rest of the graph falls. So it's going to look something like this. Okay, so again, understanding the characteristics of this graph and how to find the holes and the asymptotes is really important, and that's what I wanted to review in this example.